In part 2 of our color lecture, we'll talk about primary and secondary colors of light, additive mixing, and simultaneous contrast. To illustrate these concepts, I'm going to use this program called Virtual Light Lab, where we will look at this sphere in a black box, and behind the sphere will be a cyc. So we will see that lit up in just a moment. So the first thing I want to talk about are the primary colors of light, which we know are different than the primary colors of pigment that we may have learned in grade school with finger paint. The primary colors of light are red, green, and blue, which we can illustrate if we get up real close to an old TV and you can see those boxes of the three colors mixing together to make all the pictures on the screen. So our primary colors of light are red, green, and blue. So here's our cyc in our little black box lit up with red. Now it's important to keep in mind during this lecture that I'm using a computer program, and so the computer definition of red is a lot different than the red that we actually get from mixing with gels. But just to give a conceptual example, here is our red cyc. And then here is an example of our second primary color of light. This is our cyc lit in pure green. So here's an illustration of that pure red and that pure green light mixing to yellow light. So this is the first of our secondary colors. Red and green, two primary colors mixing to yellow, our secondary color. And next we're going to add blue and watch these three primary colors of light mix to white. So here it is. This is our example of our pure blue color on our cyc. Here we see our three primary colors, our pure red, our pure green, and our pure blue, mixing in our computer land black box to white light. And that is the definition of those primary colors of light. It's those three colors that mix together to white. They cannot be arrived at on their own. You cannot mix to red, green, or blue in light. So to illustrate a little bit the impurities of our gel, I want to use the computer version of three gel colors. So right here we're looking at R124, R125, and R126. And you can see on the graphs that they are just letting in a little bit of red wavelength, a little bit of blue wavelength, and a little bit of green wavelength respectively. So here you can see when I tell the computer to put those three primary colors, that R123, R124, or R124, R125, and R126 at full, it doesn't really mix to white. This is true on the computer and it's true in real life. It's a little bit difficult to take those gels because they are not actually the pure red, green, and blue and get them to totally mix to white. But you can see if I go back and tweak the levels a little bit, what I've done is taken the red and the blue down a little bit. I can get closer to an idea of white. On the computer here it's rendered a little bit towards gray, but that's really the lesson, is that those primary colors in our gel are not really the pure colors, and so it's hard to really get an approximation of true white light through adding gels together. So for the purposes of this exercise, I want to use these three colors, R26, 68, and 389. And if you look at the graphs of these three colors, you can see, for example, on the R26, a spike only in the red, a blue, a spike in the blue, and a green, a spike in the green hues of that spectrum. Now these are letting in a lot more white light than those cyc colors that we looked at a moment ago. The next thing I want to look at is mixing these three primary colors to find those secondary colors of light. And those secondary colors of light that we're going to find by mixing these three colors together two at a time are yellow or amber, cyan, and magenta. So here's an example of our R26 and our R89 mixing to form kind of a yellowish amber color. And here we have our R68 mixing with our green, our R89, to form our second secondary color, cyan or blue-green. And finally, we're getting our third secondary color of light by mixing R68 and our red, the R26. And you can see the magenta there where the two colors of light are mixing on the sphere. So here we're looking at something called a chromaticity diagram, which is really just kind of a fancier word for color wheel. And I know that we've all heard the color wheel before with our primary colors at 3 points on the wheel, and our secondary colors at the points where those three colors meet. On the chromaticity diagram, what's happening is we have our primary colors at the points of this triangle, our secondary colors halfway in between, and then near the center of the diagram, there's this little dot that indicates white light. What that means is that anytime you cross this diagram and combine colors from the opposite sides, they're going to mix to white there in the middle. So going back to the secondary colors again, I want to show you the three colors that I've picked to do this exercise with. If we first look at the R21, the golden amber, you can see that spike there in the between sort of the red and green areas on the transmission graph there. On the tropical magenta 346, you can see a spike on the blue end and a spike on the red end. And on R370, the Italian blue, you can see a spike there between the blue and the green sections of that transmission graph that we learned about in the last lecture. So if we imagine those three colors to be pure examples of secondary colors of light, we could imagine plotting them on this chromaticity diagram on the edges of the triangle, halfway between each one of those primary colors. So we can look at the chromaticity diagram to define our next term, which is complementary colors. So complementary colors are colors that mix to white, and those colors are across from each other on the chromaticity diagram. So the complementary color of red is going to be cyan, the complementary color of green is going to be magenta, and the complementary color of blue is going to be in the yellow amber range. So those complementary colors are across from each other on the color wheel or chromaticity diagram, and those complementary colors mix to white. So remember back when we talked about subtractive mixing, and subtractive mixing is using those gels to filter out the unwanted wavelengths of light. Now we're talking about additive mixing, and that's mixing colored light, layering colors of light on top of each other to achieve a new color. So here we're looking at an example of additive mixing to white using complementary colors red and that 370 from the cyan edge of the chromaticity diagram. Here's another example of R68 and then a blue or an amber mixing to white. Again, that's additive mixing. And finally, here's our third example of mixing our complementary colors to white with additive mixing, which is the green mixing with the magenta. So let's go back and look at that chromaticity diagram, and let's start talking about plotting colors from the gel book on this diagram. The first thing I want to look at is a pink and a red. So a pink could be said to be a tint of red, because really when we look at the graph here, it's red, it's got a spike on the red end, and it's just letting in more color. And remember that when it's letting in more wavelengths, it's getting closer to white. It's letting more white light through. So we can plot that on the chromaticity diagram as being related to that red point on the triangle, but moving in towards the white center. So I've plotted it here about halfway in between saturated red and the white point in the middle. Now let's look at the red and that pink in relationship to each other. If we look at them together on this sphere, notice how sort of the longer that you look at it, the less pink that pink light tends to look. It actually starts to look a little bit whiter because of the relationship to the red. It's losing its pinkness because it's being contrasted with red. So those two colors have many of the same traits. There's no contrast going on here except in the intensity of the color. And so after a while we start to lose the integrity of that pink color. So if we go back and look at the chromaticity diagram, we can start to talk about the relationship of these colors to each other. And remember how the pink was losing its pink next to the red. Well, the way to heighten the intensity of a color is to put it next to its complement, because that's going to heighten the contrast between each color, and contrasting them makes each color more vivid. So let's look at the chromaticity diagram and find a color that would be a complement to that tint of red, and put it next to it and see what that does. So as you can see, I have graphed out R363, which is a tint of a kind of a greenish blue. So here's what the transmission graphs of these two colors look like when they're next to each other. And you can see the spike in the red end on the pink and the spike in the blue end on the blue-green color. And imagine if you overlaid these two graphs, you'd really have a straight line letting white light in all the way across the spectrum. And when you see that on the graph, you know that these two colors are complementary and would mix to white and also contrast each other very well. So here in our little imaginary light lab, you can see how pink the pink looks now that it's not being put next to a red that shares its same traits, but rather next to this aquamarine color that is the opposite of it in many ways. The blue-green looks more blue-green, and the pink looks more pink. This is the idea of simultaneous contrast. And simultaneous contrast is this concept that complementary colors heighten the intensity of each other's color. This is not necessarily a bad thing, and it's not necessarily a good thing. It's just something always to consider when you're choosing colors for your design. So let's look at another example of simultaneous contrast. Here we're looking at blue. So this is R62, a booster blue, being contrasted with our R68, another deep blue. So we're in a world of blue right now. And if we look long enough, that R62 will start to lose its intensity. And now we're going to contrast it with R08 and see how that blue maintains its intense blue, and even how the R08 maintains a yellowy gold color being contrasted with the R62. Now, sometimes this idea of simultaneous contrast is exactly what we're looking for in our design, and sometimes it's not, and it's the one thing that's wrong with the cue that you just can't figure out what's wrong. It's just something to keep in mind and be deliberate about when you're choosing your colors.